So that was too many theorems. Maybe we need to have an example to illustrate the ideas. So let's consider the following primal and dual pairs. Okay, I want to maximize x1 subject to the fact that 2x1 minus x2 must be less than or equal to 4, 2x1 plus x2 must be less than or equal to 8, and x2 must be less than or equal to 3. So given this, now I'm going to consider its dual. So its dual is going to be, I want to minimize several things subject to two inequality constraints where they are greater than or equal to. Alright, so given this, now I want to illustrate all the conditions we just mentioned. Okay, so consider the standard form primal linear program. We're going to add several Slake variables to these three inequalities. Alright, so whatever you call them, you may call them x3 to x5, or you may call them s1 to s3, whatever. Their C is going to be 0, 0, and 0. So C transpose would be considered like this: 1, 0, 0, 0, 0. And then for A, your A matrix is going to be first these two. So you have the first part, and then the other part are for the Slake variables. So they would all be identical, identity matrix. So let's try to solve the primal program and obtain a dual optimal solution. We may do the simplex method. A few iterations later, we're going to reach an optimal tableau. So the optimal tableau look like this. We're going to say x1, x2, and x5, they are our bases. They form the basis. So x1 is 3, x2 is 2, x5 is 1. So you may verify this by yourself. And also, our primal optimal solution may be obtained like this: 3 and 2. So why we only write down 3 and 2? Because they are the original variables. We somehow exclude the Slake variables because they don't exist in our original program. The associated objective value, z star, is 3. Alright, 3 is here. So the thing is that now we are done with solving the primal. Later, we're going to show you how to solve the dual without really solving a linear program. The fact, of course, that we will rely on is the CB transpose AB inverse. Alright? So we have C, so we have CB, and we have CB transpose. CB transpose would be 1, 0, 0. Because we know XB is 1, 2, and 5, 1, 2, and 5. That's how we get 1, 0, 0. For AB, pretty much is the same. So AB is column 1, column 2, and column 5. So we collect all these columns to get AB. Maybe we would see CB transpose AB inverse would be a solution, and that would be our Y bar transpose. Let's see whether it is really dual optimal. So we may do this calculation, and you may again verify this by yourself. AB inverse is here. So once we do CB transpose AB inverse, we're going to get 1/4, 1/4, and 0. So given this Y bar solution, we may check it is indeed dual feasible. Alright? So you may do this by yourself. They have two constraints, right? For both constraints, you are able to see that the solution satisfies both constraints. And you may also see that its dual objective value, W, is going to be exactly 3, which is exactly Z star. Okay? So this somehow verifies that this Y bar is indeed dual optimal because it is dual feasible and its objective value equals the primal objective value. So it's really the case that Y bar is dual optimal. So the interesting thing is that you don't really need to know that X bar is optimal. As long as you may find a solution given Y bar here, as long as you may find a primal feasible solution that their objective values are the same, then you have shown that Y bar is dual optimal. You don't need to find that your X bar is optimal. Alright? So this somehow, in this example, we show two things. First, CB transpose AB inverse really gives you a dual optimal solution. And the second, With strong duality, we are able to verify whether one solution is really optimal or not. Okay, we don't need to run the simplex method. We don't need to take a look at whatever other conditions. All we need to know is with strong duality, there is a way to verify whether one solution is optimal or not.